Hey, this is Mr. Rosenthal here, and we're looking at section 1.2 Inductive Reasoning. In inductive reasoning, we really care about looking for patterns. We're trying to see what's happening as we move from one step to the next and develop the general rule for what we see in our specific examples. As we're looking at each step, we're going to make a conjecture. That's an unproven statement that is based on a pattern or observation. So we'll describe what we think is happening. Let's take a look at our first problem here. The first problem is wondering how many different handshakes could there be in groups of different sizes. So for example, if there's two people, then there's really only just one handshake that they could do. They could shake each other's hand. So the first person could shake hands with one other person, and then the second person, well, he's already shaken hands with that guy, so 0. If there's 3 people, there's 3 different handshakes that the first person could shake 2 people's hand. The next person can only shake 1 hand, and then the last person, he's already done, so 3 different handshakes. Now imagine a group of 4 people. The first person could shake 3 other people's hands, and then the next person, well, he could shake two more hands, and then the next person, just 1 handshake left, and so finally you're down to the last person. So 3, 4, 5, 6. Okay, let's go to a group of 5. The first person could shake 4 other hands, and then 3, and then 2, and then 1. Probably starting to see the pattern here. 4, 5, 6, 7, 8, 9, 10. I would ask you to take a second and think about, could you describe, could you kind of make a conjecture about what you think is happening in this pattern? What do you think will come next? Like, how many for 6 people, how many handshakes, or for 7, how many handshakes? Can you take a second and try to predict? Hopefully you're thinking here that it'll go 5, 4, 3, 2, 1. Right, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Another way to think about this pattern, though, besides doing it this way, is also to look at how much is it increasing by each time. So here, up by 2, here up by 3, here up by 4, here up by 5. A different conjecture you might make is that the next time it's going to go up by 6, then up by 7, up by 8, right? 2, 3, 4, 5. So if we go up by 6, 21, and hopefully that fits with the first person can shake 6 hands, 5, 4, 3, 2, and 1. Let's see, 6, 11, 15, 16, 17, 18, 19, 20, 21. So pretty cool. We've developed 2 different conjectures here, one based on the number of handshakes each person can do, and the second one looking at the pattern of how much it's increasing by, up by 2, up by 3, 4, 5, 6, and so on. Okay, so in this lesson we're going to be looking for a pattern, using some specific examples to try to develop the general rule. So we'll make a conjecture about what we think the general rule is. How does this seem to work? And then we'll try to verify it as much as possible. So here's an easier one. The sum of any 2 odd numbers is blank. Well, let's try a few odd numbers. Let's try to look for a pattern. So the sum of some odd numbers. There's a couple odd numbers. 1 plus 3 is 4, or a couple other odd numbers. How about 3 plus 5, 8, 5 plus 7, 12, 101 plus 103, 204. It seems like no matter which odd numbers I choose, the answer is always coming out even. So that's the pattern I'm noticing here. That's the conjecture I'm going to go ahead and make. The sum of any 2 odd numbers is even. The sum of the first n odd positive integers. They mean like, well, maybe let's just start with 1. And the sum just 1. Well, let's go to 1 plus 3. We're adding the odd positives, right? And so that's 4. And then let's check out 1 plus 3 plus 5. So 4 plus 5, 9. 1 plus 3 plus 5 plus 7. Let's see. 1 plus 3 plus 5 plus 7, so 9 plus 7, 16. I'm starting to see a pattern here. Up by 3, up by 5, up by 7. Also, do you guys recognize these numbers? These numbers should look familiar. 1, 4, 9, 16. I bet the next number is 25, up by 9, right? But also I'm seeing the perfect squares here. 5, 7, 9. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Yeah, so the sum of the first n positive integers, if we have one number, it's 1 squared. If we have two numbers, it's 2 squared. Three numbers, it's 3 squared. I'm going to say it's equal to n squared, the number of numbers that you have. So if you have 5 numbers, 1, 3, 5, 7, 9, 5 squared, 25. Pretty cool. Okay, so let's try to complete the conjecture based on the examples that they gave us. It says the product of any two odd numbers is, and then looking at their examples, seems like every example they did where they multiply two odd numbers, the answer always came out odd. Counterexample is to prove something wrong. So if you can find just one example that shows the statement doesn't work, we can prove it to be false. So let's try to prove some conjectures false by finding a counterexample. The sum of two numbers is always greater than the larger of two numbers. The sum is always greater than the larger number. I'm going to prove that wrong. To do that, we're going to have to think about more than just positive numbers. Maybe if we use a negative number, we can prove this wrong. How about 6 plus negative 2? 6 plus negative 2 is 4. Now they said that the sum is always greater than the larger number. Our larger number is 6, but the sum of these is 4. So the sum is not greater than the larger number. We just proved their statement wrong. It doesn't work if you use negative numbers. So a counterexample. Let's find some more counterexamples. All shapes with 4 sides the same length are squares. Well, let me think if I can draw a shape with 4 sides that's not a square. 4 sides the same length. Maybe about like this guy. I'm going to put some tick marks on here to say that all those sides are the same. So here's a shape. All 4 sides are the same length. And it's not a square because it doesn't have the right angles. Yeah, this one's actually called a rhombus. Maybe you already know that. If the product of two numbers is even, then the numbers have to be even. Can we prove this wrong? What about 3 times 2? If you multiply 3 times 2, you get 6. Now they said if the product of two numbers is even, which it is, the two numbers must be even. Wait a minute, 3 is odd. We just proved them wrong. I can get an even product even if I multiply an odd number times an even. One more here. If a shape has 2 sides the same length, it must be a rectangle. I can think of lots of shapes that have 2 sides the same length that are not rectangles. What about this one? It's got 2 sides the same length. That's not a rectangle. Or, I have an idea. What about this one? A trapezoid. This has 2 sides the same length. It's not a rectangle. So there's a lot of things that you could draw that would be a good counterexample to prove that this conjecture is wrong. All right, we're going to wrap up here with just some skills review. Take a second, pause the video, and see if you can work through 26 to 33. Try to do them without a calculator. Okay, let's check some answers. 8 plus negative 3. It's kind of just like 8 minus 3. Negative 2 plus 9. 9 minus negative 1, 9 plus 1, 3. Negative 7 minus 3. 3 times negative 5. Negative 2 times negative 7. 20 divided by negative 5. Negative 8 divided by negative 2. Negative divided by negative makes it positive. One more, pause the video. Try evaluating the expression when x equals 3. Go ahead and plug 3 in for x in all of these. Okay, let's check some answers here. So 3 plus 7, 10. 5 minus 3, 2. 3 minus 9, negative 6. 2 times 3 plus 5, 6 plus 5, 11. 3 squared plus 6, 9 plus 6, 15. 3 squared minus 4 times 3, so 9 minus 12. 3 times 3 squared, so 3 times 9, 27. And 2 times 3 to the third, 27 times 2, so 54. Thank you guys very much. I'll see you later.